Thank you, Wasong. It's a distinct pleasure for me to introduce Mike Dettinger. It's an opportunity for me to actually say a few things and maybe share a memory or two that he and I sort of have. Mike Dettinger, let me get these slides going. This is his first paper, at least the first paper that I could find on Web of Science. It was published in 1981. I believe it was from your master's thesis. Is that correct? And if you go back and look at my record, you'll also find that my first thesis publication came out in 1981, so we are contemporaries. You'll also be interested to find out that this paper, which was done as a master's degree at MIT with John Wilson, is quite well cited, and it actually has to do with groundwater modeling. I didn't realize groundwater modeling was part of his toolkit. It doesn't surprise me. His toolkit is broad. But John Wilson ended up leaving MIT, coming to New Mexico Tech, and became my friend and colleague for 30-plus years. So we have this, we share this common interest. For those of you who are maybe only more recently familiar with Mike's work, this slide has become iconic. I can't say how many meetings I've gone to where this has been displayed by multiple authors presenting. It really makes a couple of very good points, and one is the variability in annual precipitation, mean annual precipitation in California is the bullseye for variability in the 48 states. And I think this insight and these kind of things are the kind of things that Mike regularly shares with us, and I suspect we'll learn more in the presentation today. I also want to commend and thank Mike publicly for all that he has done on State of Bay Delta science, both the 2008 publication and now again in 2016. This is a collection of papers that summarize scientific understanding of the Sacramento-San Joaquin Delta. First 5 papers came out in June. I believe 3 more papers come out in September, including Mike's paper on hydrology and climatology. And then there will be 6 or so papers coming out, I believe, in December. So this is the rollout process. And this series of publications emphasizes progress that's been made since that 2008 publication. And the series of brown bags that we're having, including the last one that we had with Peter Moyle and Jason Baumstarger, was basically part of rolling out some of these State of Bay Delta science papers. And today we'll have Mike talking about really about what he's interested in, but also a little bit about the paper that is going to be published here very shortly. And for those of you interested, the eScholarship link there gets you to those papers. Okay, so just wanted to read you a brief bio. Mike is a senior research hydrologist for the U.S. Geological Survey's National Research Program, a resident scientist at the University of Nevada, Reno, and a research associate at the Scripps Institution of Oceanography. Mike has monitored and researched the hydrology, climates, and water resources of the West for over 30 years, focusing on regional water resources, watershed modeling, causes of hydroclimatic variability and extremes, and climate change influences. He's a fellow of the American Geophysical Union and a member of the American Meteorology Society's Water Resources Committee. He led the climate change chapter that's coming out shortly, and co-edited both the 2008 and 2016 State of Bay Delta science reports. I also wanted just to mention that one of his most recent publications is actually a publication on what is one of my current areas of prime interest, and that is intermittent streams and rivers. 2/3 of California's stream network are intermittent. 94% of Arizona's stream network is intermittent. 88% of the state of New Mexico, where I'm from, stream and river systems are intermittent. They don't get as much attention, and Mike, I know, has put his prodigious talents to looking a little bit at intermittent systems of late. One of his most recent publications is actually on that topic. With that, I welcome Mike. Thank you very much for being here, and I'll let him talk about climate change in the Delta.
Thanks. So as Cliff indicated, I'm really going to cheat here a little bit. I'm going to talk to you about maybe 2 slides worth about the chapter that's coming out, and the rest I just want to do a bit of a deep dive into the current drought to see for me, it was a matter of just trying to understand which parts of our systems were being hit hard and others, and which weren't so hard and that sort of thing. The kind of questions that I want to ask about the drought are listed up here. Just sort of trying to trace the drought influences through our water systems. But first, I promised Darcy that I would start by talking a little bit about the chapter on that's coming out in October. My co-authors are Jamie Anderson and Mike Anderson, Larry from the Department of Water Resources, Larry Brown from USGS, Dan Cahan from USGS and Scripps Institution of Oceanography, and Ed Maurer from Santa Clara University. Honest to God, there's not that much that you're going to read in that chapter that's going to knock your socks off or be particularly new. We've kind of been telling you this stuff for a good 15, 20 years, okay? The fact that we're still telling you this stuff should be a source of some confidence building in the sense that we're not each year changing our story. We really have kind of converged on our story, frankly, quite a while ago, and we need to take it seriously. The obvious sorts of things like likely warming by perhaps, somewhere in the vicinity of a couple degrees C by mid-century, median out of a large ensemble of projections warming in this area right here by about 4 degrees by end of century. A sea level rise somewhere out there, perhaps 80 centimeters, perhaps a meter or more, and with high-end projections right now that go well above that, 2 or 3 times that, depending on who you want to listen to. Annual precipitation remains, what will happen to that remains a conundrum. About half the models go one way for us in Northern California, half the models go the other way. But the one thing that we've kind of sort of pried apart in recent years is a better understanding that comes down to how the extremes play out. There's a near unanimity among projections that we'll have more dry days, I should say, up here in this part of the world on the whole. And those dry days will come at the expense not of the largest storms, but of the kind of middling storms. And so that at the same time that we're having more drier days, our largest storms become more ferocious, basically. And so we've got this vision of a future where we've got droughts punctuated by even nastier storms than California is used to. And all the consequences from there, more rain, less snow, earlier snow melt, larger storm-driven floods, longer, warmer summers, increased wildfire risk, and so on. In the interest of time, basically, as I said, I want to kind of dive into this drought. But first, this is the more or less unanimous stuff in current projections of climate change as relates to drought. Warmer, no big surprise, I hope. More dry days, as I just said. With the warmer cool season, we see less snowpack as a result of warmer, and in not so unanimous how much lack of precipitation feeds into that. And in warmer hot season, you end up with more evaporative demand. And that's a little bit controversial because usually we phrase the problem of what happens to water demand by vegetation in terms of warmer temperatures and the like, but playing against carbon dioxide fertilization of the plants and the like, which the warmer tends to make for more water demand. The carbon fertilization tends to counteract that. But I say it here among my more or less unanimous stuff because the thing that we typically don't toss into that mix is longer growing season. That's going to be I believe, the big kahuna in terms of what happens to our overall demand. I don't know how the balancing act between evaporative demand in the moment will play off against carbon dioxide fertilization, but I think that those longer growing seasons are going to ramp up our overall evaporative demand. And as I said earlier, all punctuated with greater risk of occasionally very large storms, so that we have this future of warm droughts and floods being commingled, as it says there. But let's get to what I really want to talk about. Let's talk about the drought that we're in right now. Here's obviously statewide water year precipitation back to 1895. And the bar is going down are occasions when the water year total was less than the long-term normal for that entire period. The ones above are years when we were wetter than normal. And you can see out there on the horizon there the drought that we're in. Basically, that figure there only goes through 2015 because we haven't finished out this water year yet. But in any event, we've been in a long dry spell there. I should note that the bar that sits the lowest there is 2014. That was the driest of the bunch, and it's not the driest on a water year basis in the historical record. There are a couple others that are drier. Some of you may have seen this form of this same story, which is what we're doing here is showing you the accumulated water precipitation deficit below a long-term normal amount over the 4 years, water years from 2012 to 2015, okay? And the way that I've mapped these out, and this is something you might have seen out there, is just accumulate them over the 4 years and ask how many normal years worth of precipitation are we behind over the course of that 4 years. So the color bar down there, the blues are places where we're basically not very behind, if at all. Actually, the whites are where we're a little bit ahead over the 4 years. Going into green, that's anywhere on the vicinity of a year behind over those 4 years. Into yellow, which is in the vicinity of 2 years, and up towards red, and deep red is 4 years, which you don't see there. We will see it again. So what I'm doing today is I was trying to really get a sense of how this signal here kind of feeds through the water system for California. And the way I come at it is very simple-minded. I just put it into I put a bunch of numbers into the same units. And one of the units I'm going to use is this missing normal years of whatever, stream flow, snowpack, whatever, hell, hydroelectric generation, those sorts of things, okay? And if you, so next. The other way that I did it, that I chose to put things in the common units is where I could, I just added up how much water we're talking about total. So if you add up all those pixels, and take them out of years behind normal and convert them back into millimeters, and then do a little bit of algebra, a little bit of conversion, we show up in that funny shaped area there. I'm not a GIS guy, so that's my version of the Delta sort of catchment area. Total missing water over those 4 years is about 313 million acre feet. Okay? Yeah, and if I integrate over the whole, that same area, and this is the only time you're going to see that area, so memorize that. But basically, if you integrate over that whole area and try and figure out how much water is missing in the missing years of water units, that little blue triangle there is pointing at the average over that area, which is to say on average over that whole area, it's basically about a year and a quarter behind, okay? So that's precipitation. Let's dive in and see where this takes us. Here are playing the same game, same color bar with the California DWR's snow courses. So this is just adding up for those 4 April 1st, how much snow wasn't there that in the long-term norm should be there. And I've put the precipitation map up in the corner there, so that, and as I say, these are on the same color bar, so you can see, kind of how this plays out. Basically, here we're seeing on the west side here of the Sierra, and that's basically the lower altitude snow courses, we're well into the red by now, okay? And so if I add all those up, I end up seeing that, in terms of this kind of just stacking each year's missing April 1 snowpack together, I basically end up with us being about a little bit over 2.5 years behind. So that's considerably more than 1.25 that we saw for the for precipitation. And let me see. Okay, next. That's just using 85 snow courses. There's a new product that's out from the folks, from colleagues at UCLA, Steve Margulis there. They put together this new Sierra snow water equivalent data set that's daily estimates of SWE, snow water equivalent, on 90-meter resolution across the whole of the Sierra Nevada from 1951 through 2015. Catch is right now, I can't get my hands on it. I can only get my hands on some summary statistics from him, one of which is being plotted here. He just hasn't released the big, enormous data set to everyone else yet. But this is this is the modern version of the snow course data that I just showed you. And you can see out there, these are each year, at each pixel, he picks out what the peak SWE was during that whole year. And you just sort of aggregate those. They're not all happening on the same day. It's at any given site, what's the peak SWE that it saw. And he adds them all up, and that's the time series there. And, of course, you can see the drought sticking out over there. And the numbers at the bottom basically are, as much as anything, just to suggest that I could use the snow course, I could use this. I'll still come up with something in the vicinity of 2.5 to 2.7-ish years behind. And if I convert everything into million acre feet, I'm in the vicinity of about minus 45 million acre feet of snow behind, compared again to the missing snowpack, which was 300 plus behind. Okay. Like I said, this is my curiosity as to what's big, what's being hit hard, what's big, what's little, and I wasn't seeing the numbers all in common units, so this is my trick to try and sort this out. This is net stream flow. All right, I shouldn't say net. This is stream flow accumulated the same way. So what's the deficit? How much stream flow hasn't been there at stream gauges that would have been there under normal conditions over that 2012 to 2015 period? I've got a combination of data sets here. One is the USGS HCDN, Historical Hydroclimate Data Network, which is basically our best shot at about 1,200 stream gauges around the country that we believe are measuring more or less natural conditions. There's no dam upstream. There's few if any diversions upstream, little irrigation upstream. We do our best to sort of identify the gauges that we think are still showing us what nature would be providing. Those are the circles, and the stars are the state of California Department of Water Resources full natural flows. They've taken the records, often on the largest rivers, and sort of backed out all those human influences to come up with their best shot at what the natural flows would have been. Again, the same color bar as up in the corner as the precipitation. And here you can see that in terms of stream flow in these missing year units, it's about 2 years behind. Snowpack was about 2.5. The precipitation was about 1.5. And you can see over there in million acre feet of water per year. I should say these are all being accumulated over that funny shaped polygon that I showed you earlier. That's basically California north of 35 north. That's how I do that. But anyway, so now we're talking some fairly big number there. I come up with a number that's about minus 90%, 90 million acre feet of water. That's not how much is missing at all those gauges. That's taking these gauges and scaling up to the best estimate from DWR in terms of how much water is normally generated in that area. So there's a certain amount of scaling going on there. If you're bored at this point, you're in trouble because I'm just going to do a lot of this for a while. Pushing on, there's water stored in a large number of California reservoirs. And basically, so what I'm mapping or plotting out here is the amount of water stored in a large number of California reservoirs. All the big ones, a lot of the medium ones, a ridiculous number of the small ones, but nowhere near all of them. But this is my sort of best shot at a representative sample. And what's being mapped out here is each month, what is the percentage of water in those in that total amount of reservoirs compared to the long-term normal for that month of year. Okay, and you can see our drought there. Not a big surprise. 2011 was quite a wet year, and so our reservoirs were quite full, well above normal, reached almost 140% of normal, and then bam, we went into the drought, and we basically, you know, get down there to about 50% of normal, or a little bit above 50% of normal. Kind of taking that apart and only looking at the end of water year storage. How much water do we have available to carry us into the following winter? That's the time series being shown here, same 173 reservoirs, and they're actually mapped out on that map there. Basically, if I accumulate the deficit the way that I have all the other variables so far, I end up with a number that looks to me like about minus 21 million acre-feet of water that's been kind of missing as carryover water over those 4 years. Eventually, I'll show you how these stacked up so you can kind of see what's big and what's little. But pushing on a little bit, just almost for grins, here's hydroelectric treated the same way. And basically, the bottom line here, you can see, oops, here we go. You know, for the state as a whole, the estimate is that we're about a year and a half, well, we're a year and a half behind normal hydroelectric power during the course of the 4 years drought from 2012 to 2015. And yes, I will get to 2016 in a few slides. For the Central Valley Project is another one where they're sort of called out. The Bureau of Recs Central Valley Project power generation, as it happens, is about, well, 3/4 of a year behind. Here's water year delta outflows basically from day flow. Basically plotted up here. And the drought is sitting over there, and it's a period when the delta outflows have been quite low. But for me, what's really remarkable is, you know, that the current drought doesn't stick out as quite the sore thumb as it has in a lot of the time series we've looked at. So, for instance, here, you know, the late 2000s was a period when the outflows were almost as low. In the early 2000s, you know, basically during this period I would say from sort of about 87 on, we're in a period there where it's really low flows compared to the historical norm over this period, with the occasional wet year that manages to push out some serious delta outflow. And by the way, down here in the lower left here is just the precipitation record sort of plotted over the same period. So you can see that the precipitation bounces around in typical California. Yeah, I can't find my cursor. In typical California style, bounces all over the place. Down here. This is day flow, delta outflow, so I believe it's pretty much as it leaves the delta, you know. Yeah. And again, just sort of converting everything I can into the same units. You see down there at the bottom that the accumulated delta outflow deficit has been about 2.7 years behind over those 4 years, and about 24 million acre-feet of water behind. Okay, I started out telling you about precipitation deficits, but you know, a large part of what's been going on is that this has also been a record-breakingly warm period. Here's the statewide average temperatures from 1895 on, and of course you can see out here in the dashed oval there that you can see the temperatures during this drought have just left. The last couple of years, 2014, 2015, just left the historical record behind. And by the way, over there on the far right over there, I've relabeled that axis with how far out in time you have to go in a 62-member 62-member ensemble of climate change projections. If you average all 62 of these projections by 31 different models under 2 different emission scenarios, how far you go out. Well, when you do that average, it smooths everything out, so you've got a pretty smooth curve as your ensemble mean. And so I can just kind of ride along that and say, oh, you know, at the temperature at this point is, I don't reach it until 2020 and 2030 and 2040. And so, you know, you see that 2015 we wouldn't expect in this 62-member ensemble until about 2040, okay? So we're getting a little glimpse of what the future might look like in that sense in a year like 2015. And, but anyway, so temperatures have also been record-breakingly high. I pointed out earlier that in terms of water years, precipitation totals haven't been record-breakingly low. We'll come back to that, I hope, at the end if I've still got time, but the temperatures have been record-breakingly high during that period. So let's think about that a little bit. We generally talk about droughts in terms of how much precipitation isn't there. That's all I've been doing to you so far. But with these warmer temperatures, what I'm mapping here is changes in the evaporative demand for water, which is it's basically the amount of evaporation and transpiration that you would get from a well-watered lawn, you know, through time. This is how much, if the water was there in a well-watered lawn, how much water would be going back up into the atmosphere. So think your Palm Springs golf course or something like that. You know, the water, it's sucking up the water into the atmosphere. And I'm playing this same game of here's our accumulated, in this case, because the temperatures are high, evaporative demand surplus. They're higher than normal, okay? I should say the equation up here, I normally don't put equations in my talks, but basically this is to show you I got nothing up my sleeves. This doesn't know about soil moisture. This doesn't know about precipitation. This is just kind of what the temperature and the solar radiation and the humidity of the air and the wind speeds and all those other things, how much water they sort of put the atmosphere in a position to accept, if you will, or to suck out of the ground surface. And so now this is a different color bar. I've been showing you all along with the precipitation and everything else to date, numbers that went from 0 on the right there over to about -4, I believe it was, on the left. These are smaller numbers, and they're positive also because, again, it's a surplus rather than a deficit. But so we're looking at about 2.5 years over my funny polygon, about 2.5 years extra evaporative demand averaged over that entire area, okay? And of course over here you can see that if I average it over that area, and it shouldn't say state, it should be the Delta catchment. And also that's a typo from yesterday. It's about 123 million acre-feet of water extra. So little flag goes off that small numbers down there on the color bar actually translate into some pretty big numbers here, and that's because our evaporative demand is typically 2 to 3 times our precipitation almost anywhere you go, and in many places it's much more. So it's a bigger number. A normal year is a bigger number with the evaporative demand. So I've shown you the precipitation as a deficit and the evaporative demand as a surplus. For me, the next it was really natural to want to know which is bigger and which is bigger where. So what I'm doing here, and this is kind of flaky, but you know, you paid your admission, so is what I'm doing here is I took the extra evaporative demand and took the precip deficit and added them up and said this is a measure of how much of this combined drought there is. There's apples and oranges going on here because the evaporative demand is, you know, we don't evaporate that much if the soil's dry. But I'm putting them, I'm saying this is kind of the potential of this drought, let's say. And then I'm asking what fraction of that total drought potential is the missing precip, okay? So anywhere where it's red, the missing precip is the whole story. The evaporative demand is a small number compared to that, okay? And where it goes to white, they're actually almost the same magnitude, okay? And then finally, when it gets into green, it's the evaporative demand is actually the big player in this drought so far. And so you see that in the Sierra, in the coastal range along the coast, you know, the precipitation deficit is the story, all right? And in part that's because there's less evaporation potential up there. It's higher, cooler, all that stuff. In part, that's where our big precipitation should fall and hasn't been falling, that sort of thing. To me, this was a surprise. I frankly figured that what I would be looking at when I mapped this out would be red everywhere. So it would all be a precipitation deficit. But when you look at the Central Valley, you can see the Salinas Valley over there, south of Monterey, that sort of stuff. It's really this drought in the 2012 to 2015 period has been kind of, it's both. It's both a evaporation drought, if you will, and a precipitation drought. Over there in the lee side, on the rain shadow side of the Sierra, you see greens showing up. And, you know, so over there, it's actually been dominated more by the extra evaporative demand than by the precipitation. And then that black blob over in the corner you should not look at. That's actually where as it happens the way I calculated, that's where instead of having a surplus of evaporative demand, you have a deficit, and that comes out of several pretty good monsoon periods there that bring a lot of moist air in and tend to shut down the evaporative demand for a while. But don't pay attention to that stuff. Pushing on a little bit, God, I wish we had good groundwater pumpage numbers like, you know, that I could Google up and use. We don't, okay? Maybe Sigma will get us to a place where we have that sort of thing, but we don't. So an obvious question is, at this point, is, well, less stream flow, less snow, less water in the reservoirs, more evaporation. You know, how much is the extra groundwater pumpage that's been going on? And we've been hearing a lot about it. Here I'm just playing a game of taking a couple of relatively long-term records, not even that long, but a couple of records of groundwater pumpage. Red ones are for the state as a whole. Blue ones are for the Central Valley. And historical records, and basically asking how do they relate to the sum of the carryover water in the reservoirs from the year before, plus the amount of precipitation that fell in the year of the pumpage that's being mapped here. And, you know, for the state as a whole, the red dots, you know, I get this wonderful looking R squared here, 90% of the variance is explained. Of course, it's a small sample size. So, you know, with the Central Valley, the R squared is lower, but it's still, you know, I'm not totally depressed by that number. When I played so what I did do is take those, well, right now I take this regression line here, the red one, and basically these arrows up here at the top, ooh, I did something bad there, the arrows up here at the top are basically for the last 4 years, or yeah, for the last 4 years I know the X value on this graph, but I don't because of, we don't keep these records in a accessible way. I don't know the Y-axis. So, but so these arrows up here are where I are the X values for those 4 years, all right? So they're way over on this side. The blue ones down at the bottom are for the Central Valley, the same sort of thing. And then I just basically use the regression line to make an estimate of, okay, here's what the pumpage ought to look like on the basis of historically how it's responded to the amount of water in the reservoir plus the precip. And you can see down at the bottom there. So just using this very simple-minded thing during the 2012-2015 period, with that simple regression line, those two simple regression lines, you would say there's roughly a year ahead of normal in terms of statewide groundwater pumpage, and about a year 1.4 years for the Central Valley. Okay, and if I can just read that off of the y-axis there, add them up. It's basically about 13 million acre-feet of water by this very crude way of trying to get at how much extra pumping we've done. I should note that those have got to be horrendously, or at least they've got to be very conservative estimates, because we know that there have been people putting in wells like crazy, new wells like crazy. This slide shows new wells constructed by year from about 1979 over here through 2015 over there for basically the southern San Joaquin and Tulare, so the southern half, southern two-thirds of the Central Valley. And you can see that, in the last couple of years, it's really taken off, okay? I have to point out, this isn't total number of wells. This is how many new ones have been added. So it's actually, it looks like, wow, it's 3 or 4 times as many going in per year now as happened kind of historically, but it added all up, it basically is somewhere less than about 2% new wells compared to the total that are just within this time period, and wells have been going on in ever since we figured out how to put them in. So, but in any event, surely with all these new wells going in and people being thrown on their groundwater supplies, that is probably, that's not captured here, and so these are conservative. That's probably the worst way to describe it. These are low. So anyway, I promised that I would sort of take on these things and stack them up a little bit so you could just sort of see. As it says down at the bottom, there's apples and oranges going on in here. Because what does an April 1 snowpack, how does an April 1 snowpack deficit compare to a overall precipitation deficit? Or there's different pieces here, but I sort of segregated them in ways that I thought the best comparisons might be made. So you can see over here on the left, this is in terms of the numbers I've been spitting at you in rapid fire form. Here's what the evaporation deficit surplus adds up to for the Delta catchment versus the precipitation. So on the whole over that big area, we saw there's about 313 million acre-feet of water for the precipitation and 120 or something like that for the evapotranspiration. So that that's what that ends up looking like. Stream flow is is a much larger number than, especially if you include in the delta outflow, then it's like 90 million acre-feet of water versus we just saw a number on the order of about 13 million acre-feet for groundwater. And similarly, the missing snow is a much larger number, well, not as nearly as much, but a larger number than the amount of missing water in the reservoirs. We get in there, we manage the water to keep frankly, keep those two reds over on the other side from getting out of hand. And this arguably maybe says that we're doing reasonably well with that. So I promised that we'd turn to water year 2016. We're not done with it. spoiler alert, we're not done with the water year yet. But so here is on the left here is our precipitation anomalies as fractions of normal October through June precipitation for this year. And then on the other side there is state average temperatures for October through June periods historically, including this year. And you can see, remember we saw that the temperatures in 2015 was a runaway record breaker. This year it's come down quite a bit, although if I could run over there and put my hand over it, if you cover 2015 up this year, you would still say, whoa, this is in the top tier. This is a very warm year that we've been in. In terms of precipitation, the greens here are where we did slightly better than normal this year. The reds are where we did abysmally, especially like down there in Southern California. But we're down there, we're like 60%, I'm sorry, 40% of normal precipitation down in the kind of LA basin area. It's incredible. But so we've got the situation, not a surprise, that in Southern California, we really tanked this year. Northern California, we kind of hung close to normal or better, or 10 or 20% better than normal. I will say that if you average over the entire state, it couldn't hardly add to anything that was closer to normal 100% if you tried. It's like 99.5% of normal or some ungodly thing like that. But we don't live at the state scale, so there are winners and losers. We already saw the figure here on the left, which is that's accumulation of deficit from 2012 to 2015. On the right, I've simply patched in the precipitation from 2016 through June. And, so up here in the north, you can see that we're getting, well, I don't know if you can see it. I've looked at these often enough that we did well. Not surprisingly, we got some extra precipitation. Down in the south, it's much more obvious that it dipped from orange well into red in much of the south. Here's our snow, treated the same way. And boy, indeed, you can't see it, but we're getting from, I have to walk away. We're getting from bright reds into deep browny sorts of reds. Basically, yeah, we've seen, especially at the lower altitudes with this continuing warmth, those numbers are sinking even further down into deficit there. And accumulated over the whole Delta region, it managed to bump things up a little bit from 47 million acre-feet behind. At the end of this year, we're about 50 million acre-feet behind. Remember, we had a not bad year at all in Northern California. It was slightly above normal in many places, but those temperatures keep eating at our snowpacks nonetheless. Stream flow. And here maybe, well, it's hard to say on this screen. Here we're seeing, well, again, the same sort of thing. It's real obvious in Southern California where we go from red, those dots down there, into virtually black over there, and with 2016 thrown in. Up north, we go from mostly yellow up there, and I really wish this here, mostly yellow up here to into the green, which is to say that we made some progress against this accumulated stream flow, missing the stream flow. And you can see the numbers down there. Our larger streams and the like are up north, and so the fact that we had a relatively good year up there, is such that it pushes this accumulating stream flow deficit down a little bit. Not a huge amount. And because looking at these map dots and trying to compare colors is hard, I plot it this way. On the bottom for stream flow, and basically, I will say that if I plot it, I used to have a slide in here that was the snowpack done this way, and it looks almost exactly the same. Here's the stream flow deficits over the 4-year part of the drought, and then over here is the same thing over the 4 years plus what we have of this year. And you can see that in areas where, so if you are a dot that's over on the right side of this graph, you were doing, okay, you were a year, maybe 2 behind, but going into 2016, whereas if you're over on the left side, you were 3 or 4 years behind as you came into this year. And so what you see here, and I should say the dashed line is one-to-one line, so any dots that are up above that have actually improved their deficit situation over the course of this year. Any dots or whatever that drop below that are, just kind of kept on their downward slide this year. And so what you can obviously see is that the places in the state that were kind of, well, a sign of how bad things have been, that a year or 2 behind sounds like we're holding our own. Places that were sort of holding their own in that sense actually improved this year. Places that were really in the tank, and that's largely Southern California, just continued their slide. A dot like that one, the very lowest one there, basically that's saying it's -4 over the 4-year period, so virtually no stream flow, and then it dropped down to almost 5 years, so just added another no stream flow year into the mix. Okay. ETO, the evaporative demand business, again, there's our temperatures. Put a little asterisk on this year. Over here, I'm mapping out the anomalous evaporative demand. That's what ETO stands for. For the October 2015 period through July, in this case, of 2016, as a fraction of normal October through July demands, okay? And basically, it's all red. So, those warm temperatures, actually along with drier air down in the south, clear skies, some more solar radiation, and actually winds, it's not clear whether they helped or hurt or how that worked out, but basically the whole area, the demands were up this year, okay? They're all red. In Southern California there on the coastal plain, Santa Barbara to LA, there were a lot in the red. In the kind of central Sierra, they were quite, a lot relative to every place around. Okay. So again, you've seen the one on the left here. That's the accumulation of the evaporative demand surpluses over the 2012 to 2015 period, and then on the right there is throwing in this year, and you can see that really it's pushed us, especially up in the north there, it's pushed us from kind of moderate values into pretty large areas there where where the numbers are starting to get rather large, almost a year behind. And remember, a year of ETO is a large number. The summer was such that it managed to push that nasty blue blob down the corner where the monsoon is screwing up my grand scheme, out of the picture for a while. But anyway, so the whole thing has drifted that way. And if we play my game again of how much of the drought forcing is precipitation, what fraction of it, then we get this. Again, on the left is 2012 to 2015. On the right is 2012 through 2016. And basically, I mean, the whole, Nevada just sort of goes green, which is to say, over there it got enough precipitation, and while the evaporative demand continued in this anomalously high amounts, that it pushes us over to where, if you consider the 2012 through 2016 drought, it's by now, it's an evaporative demand drought. And that's a big change for just throwing 1 year on the end of a drought. in the central, well, in the San Joaquin Valley in particular, we go into that mode too. And remember, that's an area where this year they did not do well in terms of precipitation. So the evaporative demand is just pushed the precipitation deficit aside in the San Joaquin and southern Central Valley. Yeah. And, yeah, okay. I should maybe go back and just say, you know, and if you look at the totals, when I add it all up in terms of million acre feet, that's a big jump. That's, you know, that's whatever that is. That's about a quarter jump or something like 25% jump. That's a large number for throwing in 9 months or something on the end of this drought. Okay, so the left-hand bars here are the ones I showed you before, and now I'm just laying out what happens when you throw in this year so far. And you can see the large jump. Well, the precipitation just, you know, accumulated this way on for this large delta catchment area. Just, you know, there's very little. Well, the improvement we got, you can hardly see. You have to look hard to see it, put it that way on this graph. The ETO is a big jump there. You can see that. My best shot at you know, groundwater pumpage, given that I know what the carryover was in reservoirs into this year, and I've got pretty much all the precipitation we're going to get this year. Looks like, you know, an increase there. Stream flow improved a little bit, but all of these numbers, with the exception basically of that number right there, are really marginal changes. And that's, you know, just that we had winners and losers, and they all kind of averaged out at this large scale. So finally, to bring it back home, droughts this time versus droughts of the future, I just wanted to make a couple comments. You know, this time we have this record-breaking warmth during this drought. As I said earlier, you know, we're looking at temperatures in the last few years that are in the vicinity of what we would expect in the 2030s and 2040s in current climate change projections. In 2015, we had this absolutely terrifying 5% of normal snowpack, April 1 snowpack. I mean, honest to God, we've been making projections of these losses of snowpack for years, and I honestly never could imagine. I realized when I saw the numbers for 2015, when they started emerging, that honestly, even though we've been talking about it for years, I really had never kind of conceptualized, you know, what it would take to get to a 5% of normal SWE year. It's amazingly low. Well, a couple of years behind in terms of stream flow and outflow from the delta, that sort of thing. And then one other angle that actually Mike Anderson pointed out to me as I was, while we were working on the climate change chapter and trying to, grappling with this drought, was I've told you several times that the water year totals of precipitation have not been record breakers over the last 120 years. But if you forego the water year and just say, let's look for periods, you know, any period that's a long period within this drought, and compare that to the historical record. Are there record-breaking chunks of time in this drought? And in particular, when you do that, for instance, you can find a record-breaking 13 or 14-month period that was from. Well, I'm going to talk about the 13-month period that was between January 2012 through January 2014. Hold on, I'm almost at the end. Let me wrap this up. No, seriously, put your hand down. Let me wrap this up, okay? I'm right there. That period was the record breaker, and indeed it was only 35% of normal January through January totals, okay? And the next lowest one in this 120-year record was 53%, so 20% more than this. So this was a standout 13-month period, and it has the characteristic. This is what Mike pointed out to me, was that it really began right after a major atmospheric river storm. I'm showing you there the North Fork American hydrograph. So it began right after a major atmospheric river storm, and it basically ended with the arrival, finally, of another major atmospheric river storm. And, you know, so if you've seen these things, the bright colors are where the water vapor in the atmosphere is, and where it's really, you know, and that's an atmospheric river coming up out of the tropics and slamming into Northern California in both cases. And so, you know, I started out by saying that you know, the future drought will be, you know, these drier, warmer, or kind of more persistent, warmer droughts punctuated by large storms. And, you know, we have in the midst of this drought something that looks like what you might want to imagine these future droughts looking like. So you're first up, but so in this drought, precipitation and temperature, ET aspects have vied with each other to determine how severe the drought is. And we were, you know, over much of California, the precipitation deficit was the whole story until this year when we had a kind of normal-ish precipitation year, and with the temperatures staying up, boing, you know, large parts of California, and as I said earlier, you know, most of Nevada just flipped over to where they, really, on the whole, this has been an evaporative drought instead. These drought deficits measured in kind of common units, and in particular my silly years of missing water units, but you could do it with percentages. You could do it with standard deviations to an extent. A lot of those things, they basically amplify as they pass into and through the water system. That shouldn't be a surprise to anyone, but this is part of what I was struggling to try and get my head around. Precipitation drought, the regime of this drought is severe drought, punctuated by a few intense storms, and that's something that we look forward to. I'm not sure that's quite the phrase that I want, but you know, that's what we anticipate. And so, and I would say that as climate change takes hold, these temperature effects will become even more important. And for me, the rapidity with which certain areas kind of flipped over from having from what I would consider now to be an evaporative drought from a precipitation drought suggests that that isn't something that's way off in the future. We can do that, you know, in this drought, we see it happen. We can do that almost any time now, and it's only going to get worse as we move into the future. So finally, yes? Pardon me? Yeah, okay. That one?
I wonder whether this is 2030.
Oh, I'm sorry. Wait a minute.
Oh,
no, you're right.
Or into 25 years.
No. Yeah, that is a typo. What the hell did I do? That would be beginning in, well, let me look at the figure. Okay. Yeah, look at the figure. That is a typo. Basically 2013 to 2014.
Oh, yeah.
Thank you. Sorry, no, thank you. Yeah. Yeah, it wasn't 25 months. So, any other questions?
So if you have a question, raise your hand and use the mic.
Mike, have you driven around the Sierra, and are you surprised that there are any trees left at all? I know you didn't go into soil moisture and forest hydrology, but how are any trees surviving such a drought?
So one of the slides I took out is, that question, because I have driven around the Sierra, and frankly, for the last 3 years, every year, various of my colleagues, Roger Bales and folks like that, we end up getting together and saying, one more year and those meadows and those streams are toast. And frankly, each year, we've kicked ourselves and said, I don't know where the water is coming from. The trees are definitely, they're in trouble. And that's probably part of the answer for why the streams and meadows have survived as long as they are, is that as the trees die, that reduces the amount of draw on some of that water and allows some of the system to do better than it would otherwise, I suppose. And I'm not a tree person, so that's a total guess. But so what I did here, here's our precipitation deficits, here's our stream flow deficits, and here I simply took the September flows, figuring by that time of year, you're kind of looking at the low flows in most of these streams. Maybe not the lowest flows, but I don't have to contend with storms and stuff for the most part. So this is my base flow. And I play my usual game here of looking at the base flows here. And so these are the September deficits. This is for 2012, 2015, because we haven't gotten through September, that's why I don't have 2016. And again, now these are all on the same color bar. And basically what you see here is, in terms of comparing the stream flow, that it's tipping well into the red, so that, so that the base flows have been doing more poorly in these kind of relative terms than the overall flows. Probably not a surprise. But if that's in the southern Sierra. As I move up into the northern Sierra, actually they've done somewhat better. And honestly, I'm not sure what that's about. As I say, one of my pet theories is that when I drive out and see all the dead trees, it's like, well, fewer straws in the cup. But yeah, so this is about as close as I can get with the kind of data that I play with to getting to this business of how the Sierra have done at this sort of forest. And I rely on the JPL folks and the like to tell me how many dead trees there are and that sort of thing. But, yeah, so I think it's really curious that these base flows, this is kind of an amplified version of the gradients in here. And so in central and northern Sierra, the base flows haven't dropped as quickly in these kind of relative terms as the overall flows, which is largely, springtime flows and the like. That's not an answer, but I'm thinking about it.
Part of that being that in the Northern California corners up there, you have different geology and you have a lot of interstitial flow coming back through the fractured rock, and basically these low, cold water systems that are perennial. Yeah, no, that's true. And I know that like PG&E and others, PG&E in particular has kind of made its living for years or however long they've been around by relying on the fact that when everything else is dried out and gone, those volcanics up there still kind of steadily release water. So, yeah. Yeah, it is. One more. Sure. You would take a leap. How would you overlay onto your great graphics here? How would you overlay estimates of regional water demand? And the fact that we've got different water balance in the north and the demand is in the south.
I have an answer to that. Yeah. I don't think I have an answer to that. For me, living through this and seeing, that this corner of the state has kind of done reasonably well even during the worst of these years, and I'm stunned by how low those numbers are, even though I probably shouldn't be. But yeah, no. I think the whole state's been taking it. Yeah. I don't know. I mean, I'm not going to pretend that I know exactly, but no, I don't think that it shows up anywhere short of maybe the Great Plains or something. That would be my guess. Remember that a lot of the ET, most of the ET is happening in the warm season, and, you know, we don't get the precipitation then. So there's this seasonal displacement between when the water is available and when it's not. So you have to kind of go look to where it's precipitating when most of this ET is happening. And I think the Sierra.